Okay, good evening, everyone. Welcome back to this Rediscovering the Space, Challenges and Opportunities in the Aerospace Research and Business Sectors at Politecnico di Bari. As a coordinator of the PhD program in Aerospace Science and Engineering, I'm really happy to see that this cycle of seminars is arousing large interest in the community. So I really thank all of you for being here and again. You have seen that we have tried to offer a very multifaceted program. We are trying to cover a wide range of topics, but today, in addition to be very interested in the talk, I'm also very excited to have a special guest, a young and brilliant scientist. He is native of our land, Puglia, and he plays a very important role at NASA. A reference point for aerospace research in the world. So I'm sure we will enjoy the talk. So just the recurring technical note. After the talk, if you want to interact with the speaker, we will give you the permission. So just ask on the chat that you want to make questions. So you don't need to write the questions, just ask for it, okay? So finally, I give the floor to the moderator of the talk, Francesco Loparco, professor of experimental physics at the University of Bari. Francesco will introduce today's speaker, Giuseppe Cataldo, lead mission and instrument system engineering at the NASA Goddard Space Flight Center. Giuseppe, thanks a lot for being available. It's a pleasure to listen to you. So Francesco, please take the floor and introduce Giuseppe. Thank you.
Good afternoon to everybody, and welcome to this seminar. Today I have to say that I'm really honored to introduce our speaker, Giuseppe Cataldo, who is, as Marco said, a brilliant researcher, and before being a brilliant researcher, he was also a brilliant student, as I can see from his curriculum. Just some hints about Giuseppe's curriculum. He was he started working at NASA in 2009 when he was still an undergraduate student, and he was selected among the most brilliant students for a NASA Academy program. Then he has been working at NASA for more than 10 years, and I see that he is involved in several important space missions organized by NASA. In particular, he has important roles in the James Webb Space Telescope, which is the instrument which takes the inheritance of the Hubble Space Telescope. He's also involved in several other missions. In particular, I see that he's involved in the OSIRIS-REx mission, which probably some of you have heard about in 2020. It was a NASA probe which collected a piece of an asteroid, and that it is supposed to come back in 2023 on Earth, right, Giuseppe?
Mm-hmm. Yes.
And as you can see, Giuseppe has covered several leadership roles in all these missions, and also he has been awarded of several prizes. This is a very remarkable curriculum. So I'm very happy to give the floor to Giuseppe and to listen to his presentation. So Giuseppe, please go on.
Okay, well, good afternoon, everyone. It is a pleasure to be to be in Puglia, although virtually. Very happy and to be there with all of you, and thank you the moderator and Professor D'Artuglio as well for the kind invite to join this a series of seminars. Okay, so I think we can get started. I think you can all see my screen. So I'll start the show. Today I'll be talking about the space telescopes, which has been the focus here over these past years at NASA. I think what I'm going to do is like provide an overview of some of the projects I've been working on, and then some of the future space telescopes that we will be developing, and then I'll focus more on the James Webb telescope. All right, so all of you know Hubble, the Hubble telescope, and the great discoveries that it has made over the past 30 years. Here you can see at the bottom a nebula, the Carina Nebula, as we see it with our eyes, and then here the same nebula seen in the infrared. So you can see basically that all the dust and gas basically disappears in the infrared, meaning like, you know, with the infrared light, we are able to get through the dust and therefore see what's hidden behind. And what's hidden behind is a lot of stars and possibly planets that might be forming right now. So Hubble is really our workhorse. You know, here is a picture of the Hubble's ultra deep space field, as was delivered in 2014 with the data from the ultraviolet to the infrared. So it's actually a collection of pictures. Here you can see something like 10,000 galaxies just in this picture, which is a very, very narrow part of the sky in the Fornax constellation. So we have a lot to learn about the universe. You know, this picture is, you know, one of the oldest, shows really some of the oldest objects in the universe. And therefore we're really intrigued by you know, really the history of the universe, you know, how it came to be, how it evolved, and how we made it, you know, to planet Earth somehow. So it will show like the history of the universe in a snapshot. So right now, so we are here at the right of this picture. That's like the present day, and then we can go all the way back about, you know, almost 40 billion years ago, when everything is thought to have started with, you know, the Big Bang, and then it's a very rapid inflation that happened in a tiny fraction of a second. And then, you know, many other physical phenomena happen, and I won't go into right now, but we can claim that for many years, you know, for about 400 million years, we have what we call the dark ages. So the light and the matter were all together, and the first stars really didn't come to be before this moment. So at around 400 million years, so we can say, we think that that's when the first stars were born. And then from there, you know, it was the development of galaxies and planets and solar systems like ours, all the way to present day. We can see that the universe expanded very rapidly and then decreased, kind of slowed down in its expansion, but the expansion started to accelerate again. Something that, you know, we think probably due to dark energy, but you know, still like one of the open questions that we have right now. So I think, you know, what we want to do right now is really to kind of, you know, go all the way back as far as we can, okay, and try to detect the first light, the light of the very first stars. And that's really why we need something like James Webb, whose main goal will be really to look at the first light, and then study also the development, the evolution of galaxies, planets, solar systems, and possibly try to answer the question really how life came to be. Okay, so we have telescopes really a little bit all over the place. We have telescopes down here on Earth, and then telescopes on a plane, on the balloons, on the rockets, and then in space. Okay, that's really due to you know, the effects of the atmosphere of our planet. So you can see here, you know, the fraction of radiation is blocked by the atmosphere of our planet. You can see a few windows that let the electromagnetic radiation come through. So in particular, we have the radio window that the atmosphere is completely transparent to, and so we have a lot of radio telescopes right here on the ground. We have the visible window, of course, where we can see with our eyes. Usually, round telescopes, are built in the desert areas or like at the very top of mountains. Exactly because we want to avoid a couple of problems. One is the negative effects of the atmosphere. So like the higher we go, the better it is, because we can get through like above most of the atmosphere, and then also desert means like dry air, so we don't suffer from the negative effects of the presence of water and turbulence in the atmosphere as well. Then in order to be able to see the light in other windows, namely the infrared, the microwave, and so forth. I mean, we need to get higher and higher, so that's why we use balloons or rockets, and then the best is definitely going up to space, right? So here you can see a few telescopes in the gamma ray, Fermi, Chandra in the X-ray, Hubble in the visible, and Herschel, Spitzer in the infrared. We got many over there. Okay, so now what I'm gonna do really is like to guide you through a few of these telescopes. So I'm gonna go from the ground, and then you're gonna go, to the sky, and then up, or farther up in the atmosphere until we leave the atmosphere and go to space. So one of the projects that I'm leading right now is the prime camera for the prime telescope, which is being built in South Africa at the present moment at an altitude of around 1,800 meters. This telescope will, it's a relatively small with 1.8 meter primary mirror. It's an international collaboration led by Osaka University. At Goddard and NASA Goddard, where I work, we are developing the near infrared camera with H4RG detectors, whose objectives are basically to perform microlensing survey of the sky in preparation for the microlensing survey that the Roman Space Telescope will do after it launches around 2025, and I'll talk about the Roman at the very end of this presentation. Okay, so that's an example of instrumentation that we developed with detectors that have to be cooled down to around 80 Kelvin. Therefore, the need for a dewar and cryocoolers to reach such low temperatures in order to make the detectors be sensitive to the infrared light, especially from the ground. Then we can go a little bit up. So we have Sophia. So Sophia is really like a telescope on a plane. Sophia is a Stratospheric Observatory for infrared astronomy. It flies here on a modified Boeing 747 and carries a 2.7 meter reflecting telescope. So it flies in the stratosphere at an average altitude between 11 and 14 kilometers, which is like roughly above 99% of the Earth's infrared blocking atmosphere. So we really, we are able to really detect such wavelengths by going up just a few kilometers. Sophia is very practical because it allows scientists to look at events that take place, for example, over oceans where there are no telescopes, apart from Hawaii. I mean, it's still a round telescope there. So usually we have 10-hour-long overnight flights. And really the fact that we can fly the telescope allows the scientists to look at phenomena from almost anywhere in the world. You might have heard recently about the discovery of water on the sunlit surface of the moon a few months ago. But again, Sophia looked at many other events like eclipse-like events of Pluto, Titan, Kuiper Belt object MU69, and other phenomena. Then we can going up or farther up in the atmosphere, so balloons. Right now, we are working on a few balloon missions, but this is the one that I'm leading actually as the chief engineer. And so EXCLAIM is the experiment for cryogenic large aperture intensity mapping. It's an infrared balloon-borne telescope with a 1-meter primary mirror. Basically, the infrared light enters the telescope through this aperture and then goes through a series of kind of following a path all the way down into what we call the receiver, at the bottom of which there are 6 spectrometers. Like this one here. This is a very revolutionizing technology. This spectrometer is the size of a credit card. That's how small it is. You can hold it in your hand. It's been in development at Goddard for almost 10 years now, and it was actually the object of my PhD thesis. At MIT, the live ones, it arrives here, it's captured through the antenna, propagates through this delay network, and then reaches the multimode region where the light diffracts and reaches the other side where we have a lot of receiving antennas that connect the light through MKIT, microwave kinetic inductance detectors on this side. So this is all developed on a silicon, so it's a silicon chip and then all that you see here in this picture is basically photolithographed on superconducting materials. EXCLAIM will fly in the upper stratosphere at around 30 kilometers. You can see a few thermal shields that protect the balloon from, really the instrumentation from the radiation of the Earth and of the sun. So here I'm going to show a few pictures of from another mission, the Piper mission that was flown a couple of years ago from Fort Sumner in New Mexico. So here you can see the telescope right here hung on this truck that delivers it to the field, and then it makes it fly. Here you can see a picture at float altitude about 30 kilometers, like I said, of our planet, the sun. And here you can see one of the thermal shields of Piper. So ballooning is actually very fun, and it offers a lot of advantages. And in particular, the fact that we can reuse the balloon multiple times. So that means that we build a telescope and we can fly it multiple times and do a lot of, so that allows us to actually lower mission costs by reusing all the hardware. It can be very, very, very practical. But now going even further up, so we leave our planet and we go to space. So I think the beginning of this presentation will be about the James Webb Telescope, which really we think of it as the future of astrophysics in space. So Webb is it's an infrared telescope. Will succeed, as you say, the Hubble, and will launch no earlier than October of this year, if all goes well. It is an international collaboration between NASA, ISA, and the Canadian Space Agency. There's a lot of different parts here. So we can see the primary mirror in the center, so the main eye of the telescope, the secondary mirror that reflects the light into the tertiary mirror, and then allows the light to propagate all the way to the back into the integrated scientific instrument module where the instruments are located. You can see here a big sun shield that protects the telescope from the radiation of the sun, and then the spacecraft bus, which we can compare to, like, the brain of the telescope. James Webb was the second NASA administrator, so we decided to name the telescope after him because he was the one that oversaw the Mercury, Gemini, and Apollo programs, and he inspired NASA scientific program, even if he was not a scientist or an engineer. And I think something like 75 space science missions flew under his administration for the very first time. So we are talking about the beginning of the space era. Webb, so the mirror is something like 3 times bigger than Hubble. So here you can see a comparison between the Hubble primary mirror, 2.5 meters, and James Webb. So it's actually one mirror made of 18 smaller segments that altogether will function as one big eye. So bigger and stronger because the bigger the aperture, the more light we can detect, we can capture, and so we can increase the resolution and look at also very faint and far distant objects. So here you can see a comparison of just to give an idea of how big it is. So the sun shield is like the size of a tennis court. So it's like 21 meters long and about 14 wide. So you can think already of the engineering challenges of building something this big, and also to fly something like big. There's no rocket right now that can fix something like that. So but I'll talk about that later, how we're gonna fit it into our rocket. So the mirror, so like I said, the light gets captured by the primary mirror, gets reflected to a secondary mirror here, and then goes into this black box that contains a tertiary mirror, and then goes all the way to the back where the instruments are. 18 segments, each one of which has 6 degrees of freedom. So they can move with respect to each other around X, Y, and Z, and then can rotate around the 3 axes. And they can also change their radius of curvature through some piezoelectric actuators that they have in the back. So they are made out of beryllium. Why? Because beryllium is 6 times stiffer than steel, but 3 times lighter than aluminum. So each segment weighs only 20 kilos. But probably even also, almost more importantly, I would say, beryllium is very stable from a thermal perspective, and that's really what we need. We fly a telescope from our planet all the way to space, where they're gonna feel the effects of thermal contraction, and beryllium allows really really so stable that the mirror will not deform and will remain pretty much in the same shape with minimal variations. So it looks yellow because it is gold coated. So there's a very thin layer of gold to increase the reflectivity of the mirror, and it will work at a temperature of 40 Kelvin. Okay, just to give you an idea, so if James Webb were on the surface of the Earth looking at the moon, and a candle were lit on the shady side of the moon, James would detect it. So that's really how powerful James Webb is going to be. And see 1,000 times better than our eye, than the human eye. So this is like a model of the piezoelectric actuators that are in the back of each segment to allow, like I said, each segment to move and eventually to kind of make sure that the 18 segments will operate like just one mirror. Okay, now we can look at the instruments. So this is a picture of the instruments. So we have basically near infrared spectrometer, near infrared camera, mid infrared imager, and then fine guidance sensor, and another near infrared spectrograph here. So the instruments really can be thought of as the retina of the telescope, right? So the mirror captures the light, and then eventually the light gets focused on the focal plane of these instruments here. So pretty much like the retina in our eye. So very sophisticated instruments, and I think so near spec is actually a contribution from the European Space Agency. So I'm gonna talk about some of the technology that was developed for Webb. In particular for the near infrared spectrometer. the near spec will allow for the very first time to perform what we call multi-object spectroscopy. So we can look at around 100 targets at the same time. And how is that possible? It's possible through these micro shutters that you see here. These are really very tiny windows that open and close through micro electromagnetic systems, so MEMS. And by opening and closing, they allow basically to let the light enter only the light of specific objects that we want to look at the sky. And like I said, something like 100 targets at the same time. So to give you an idea of how small this is, like this chip is the size of a stamp. Okay, so imagine to have like a stamp in your hands and to have like 60,000 windows in this tiny stamp, okay, in your hand. That's really like how small the micro shutters are, and it's really incredible. Okay, moving on. So I mentioned the fact that the telescope will work at around 40 Kelvin, right? So minus 230 degrees Celsius on the cold side. But we have the sun, which is a big star, and emanates a lot of radiation, and so the hot side will be at a temperature of around 85 degrees Celsius. So that means that the sun shield will have to make the temperature decrease in a totally passive manner from 85 degrees to minus 230 Celsius. So that's like a huge, very big thermal gap. And well, the layer will allow us to achieve this, like I said, in a completely passive manner, because it is made of 5 different layers. Okay, each one of which will allow the heat to well, be sent out through the gaps that each layer has in between. And also through a lot of reflection, by reflecting the radiation of the sun back into space. So the reason why we have to be at this cold temperature is really because we want to detect this very faint infrared light, and infrared is synonym to heat, right? Thermal radiation, and like I said, we are going to look at the very first stars, and they are very far away from us, very faint. We want to make sure that we are able to detect it. But not only that, the spacecraft bus. Also, that's where all the warm electronics is located, so that also emanates a lot of heat, and that's why we need to make sure that all the heat generated by the spacecraft bus also gets, kind of well isolated, from the mirror and the instruments. Only one instrument will work at 6 Kelvin binary, and then will be actively cooled through some very innovative cryocoolers. Okay, a little bit. I'm gonna provide a more detailed view of the sun shield. So you can see the 5 layers here. So each one of them, except the first one here at the bottom, is about 0.025 millimeters thick. So very, very thin, actually. They're all made of capton, because capton is a very high heat resistance, and it's a very thermally stable. Each layer is coated with aluminum, which is highly reflective, and then doped silicon, and actually only the first 2 layers, the one at the bottom here, because well, silicon has a very high emissivity, and then doping the silicon allows the layers to be actually to become electrically conductive, and therefore they allow the sun shield to be rounded to the rest of the telescope. And so all this like electrical charge, we don't want that to accumulate. So each of these material really plays a very important role. And then, so just a curiosity here, so you can see also, like I said, so the heat will be reflected off each layer, will be sent away also through the gaps in between. Also, like, the vacuum in between each layer, that's a very good insulator as well. That's why 5 layers are better than just one big thick layer. The fifth layer actually is mostly for margin against imperfections of the four lower layers, but also it will protect the telescope from micrometeorites, holes. So it's another protection that we have there. Because well, in orbit, I'll talk about that in a moment, but space is not perfectly clean, right? So we have always like space debris wandering around, and the sun shield will, one of the it's not only about thermal protection but also protection from space debris. That's why you can see some of the structure here in the shield, the structure here that are serve as actually reinforcement of each layer. So like imagine that like a micrometeoroid hits the shield and makes a hole. So the hole may actually become bigger and bigger, right? It can be like and having these kind of structure here, these rims all along allows these rips, tears to actually remain limited. And so that's like another protection, because if the sun shield breaks, then clearly radiation will make it through the telescope, and the temperatures will no longer be 40 Kelvin, and we don't want that to happen. Okay, so where are we gonna launch it? So Webb will leave at around 1.5 million kilometers from our planet. So it's like much farther away from where Hubble is right now, at around 570 kilometers at the Lagrange point number 2. So for those of you that might not be familiar with this particular orbit, but this orbit is very, very special for many reasons. Lagrange discovered 5 Lagrange points for every 3-body system, so 3 of them are perfectly lined up, as you can see here, for the Sun-Earth system, L1, L2, and L3, and then we have L4 and L5, and they form like 2 equilateral triangles. For Webb, okay, why did we choose L2? So L3 would be problematic because we would have the sun in between, so we would not be able to communicate with the telescope. L1 is too close to the sun, and we don't need that, because we need to be really as far as possible from the sun to achieve those cold temperatures. L4 and L5 actually have another problem, the fact that L4 and L5 are stable points of equilibrium. That means that things accumulate there. They accumulate, and therefore we can say that they're kind of dirty points, and that's a problem for James Webb, because, like I said, we don't want micrometeorites or space debris to hit the telescope. So L2 has none of the disadvantages of the other 4 points. It's far away, so provides an effective cooling for the telescope. Has no debris because it's an unstable point. That means that any debris that ends up there will naturally drift away. Also, these points are very special because it's like the gravity of the sun and the Earth basically we can say that cancel out. Therefore, the telescope will follow the Earth around the sun. Okay, and so the distance between the telescope and the Earth basically remains constant. And this means that the data rate that needs to be maintained, we can do that with the same large round antennas of the deep space network. And then most importantly, also I think being here allows Webb to be like not to have the moon, the Earth, and the sun kind of obstructing its view, and so it's gonna have like a complete view of the sky, which is really good for the types of observation that it's going to do. So it will launch on an Ariane 5 rocket from French Guiana. So in French Guiana, well, first of all, that's the launch base for ISA. But French Guiana is also good because it's very close to the equator, which is equivalent to say that we can launch the telescope with more momentum, and then also it's good for orbit insertion. So we chose this launch base exactly for these two reasons mainly. Here you can see already a glimpse of how we're gonna fit the rocket into the fairing of the we're gonna fit the telescope into the fairing of the rocket. So James Webb is gonna be folded up. So you can see the shield here folded up, even the mirror will be folded up, and that's actually the reason why we had to think of a mirror that can actually become smaller in order to fit into the fairing of the rocket. So like an origami. So I'm gonna show a series of pictures here very quickly that shows a little bit the construction of James Webb as it happened around 5 years ago and at Goddard. So here we are in the clean room at Goddard. You can see one of the 18 segments attached to a robotic mirror. And you can see here as the robotic arm, and the robotic arm is placing the mirror on the back plane, so that supports all the segments. Here you can see all the 18 segments placed on the back plane and covered to reduce contamination. And here you can see the clean room and the window here from which we used to stop every day afterward to see how things were making progress in the clean room. Here you can see some engineers uncovering the mirrors, and here you can see the primary mirror and the secondary mirror completely uncovered, where everything was finished in order to perform some optical tests. Okay, so yeah, this picture shows me kind of dressed up before entering the clean room with my boss at the time, and me next to the picture here to say that really I was never really expecting to work on a project like this in my life, but it happened, and I'm very honored to have been a part of this. Then after that, Webb moved on to a series of testing, vibration testing, acoustic testing on this vibration bench basically that simulated the launch environment. So simulating all the vibrations that Webb will feel during launch, in the rocket. And then he came, time came to say goodbye to James Webb. Here it is in this, white container entering this plane before we flew it from here in Washington to Texas, to Houston, okay, where we said, hopefully we won't have any problems there because James Webb was gonna enter a series of tests that were gonna simulate actually the space environment in this vacuum chamber that was the same that was used for the Apollo missions. Okay, so it was refurbished for Webb. Here you see the Webb, actually the mirrors in their deployed configuration, and then inside the vacuum chamber where we simulated, the pressure and temperature environment of space. So everything went very well. And eventually Webb was brought to California for final integration with the sun shield, okay, and for the last series of tests that it is still undergoing at the present time. So like I said, we are close to finishing these tests and then shipping the telescope down from California to French Guiana through the Panama Canal on a barge. Okay, so that's really what we are looking for. And so if I'm allowed to show a very brief video of launch. So I'm gonna comment it. So the launch, like I said, will happen not earlier than October of 2021. So here you can see the separation from the rocket. about 30 minutes after launch, and then the deployment of the solar array that will be the main energy source for Webb. There will be a few here kind of orbit corrections and slew maneuvers for thermal stability of the telescope. The antenna, the high gain antenna, will deploy, and that will allow us to communicate with Webb. So after about 3 days, we'll be past the moon, and then we can see the deployment of the sun shield as it travels, toward the final destination of Lagrange point. So the aft and the forward sun shield. So the mirror will separate even further to allow the additional thermal isolation, and then you can see the deployment of every layer of the sun shield. So you can see the boom here coming out and pushing the 5 layers out. So all the membranes will be tensioned, and then they will start separating from one another one by one. And then we have a momentum flap, management flap here that will deploy, followed by the deployment of the secondary mirror. The carrier cooler starts in the meantime. So Webb will start cooling down, as it goes to orbit, to find the final orbit. So it's the deployment of secondary mirror and one of the wings that will complete the primary mirror. Here's the other, and then finally all the way out to Lagrange 2 point before it begins kind of actually traveling around what we call a halo orbit. That is will take about 6 months to kind of perform full orbit around Lagrange 2. Like I said, will follow the Earth around its path around the sun. So now I'd like to say a few words about technology development that was made for James Webb. There have been a lot of spin-offs from all the technology that has been developed for Webb. So funny enough, Webb contributed to improving some of the technology actually on Hubble. So that's funny how a future mission helped a currently operational mission to become better. So some of the application-specific integrated circuits that were developed for Webb were actually used to improve one of the instruments on Hubble. So very interesting. So the infrared sensors developed for Webb also have now become the universal choice for astronomical observations, both from space and the ground, as well as for application in like Earth science and national security. A lot of commercial application, especially in the semiconductor and medical industries. Here you can see a laser interferometer that was developed for wavefront control in Webb. And then finally, medical applications. So a number of improvements in technology have been used already for the measurement of human eyes, for the diagnosis of ocular diseases, and potentially improved surgery. So this is really amazing whenever I think about it, that already now we can feel, we can experience the benefits of all these technology developments. Okay, looking beyond, so as I mentioned before, we're already working on the successor to Webb called Roman. The Roman Space Telescope will be mostly focused on dark energy and exoplanets. It's pretty much like the size of Hubble, but it will also orbit in the same orbit as James Webb, L2, and we don't plan to launch it before 2025. The great thing about the Roman is that it has a field of view that is like 100 times larger than Hubble. So you can think about the scientific productivity would be increased by a factor of 100. We can look at the same in an area that's 100 times larger than what Hubble can do right now. And then you will have a coronal wrap instrument to do high contrast imaging and spectroscopy of exoplanets. So it's like a really amazing field now of research that you hear about in the news about all these planets that are being discovered around other solar systems. And then looking even beyond Rome, looking like more what's happening in the 2030s. Right now, I mean, we have basically 4 concepts that are being evaluated. One of which is LUVOIR. So you can see here in the picture, it's like a much bigger James Webb. Right now, there are 2 concepts. One with 15-meter primary mirror, which is what is here right here. With 4 instruments that can be serviced. So the idea here is that if you're going to build something like this, so big, so complicated, that might fit into some rockets, but especially when we think about James Webb, that once we launch it, there's no way we can go there to fix anything. So we are thinking about ways to actually make the instruments serviceable by robots. So we can send a robot there. We maybe like astronauts pretty much did with Hubble. Okay, so the astronauts changed. Well, first of all, they fixed the primary mirror of Hubble after it was launched, and they improved some of the instruments that Hubble had over time because technology moves fast. But we have never flown any human being. 1.5 million kilometers from Earth. And so if we can do this with the robots, that would be really great. And so we are already thinking about how we can develop telescopes that are serviceable, and maybe in the even more be able to actually assemble themselves autonomously in orbit. But that's really for the future. I think really the bottom line is that spaceborne telescopes, balloons are really the new frontier for infrared astrophysics. We go from Sophia to Webb pretty soon, with CLAIM coming up in 2022, Roman in 2025, and eventually one LUVOIR or one of the other 3 concepts that are being evaluated right now in the 2030s and beyond. There's really a lot to expect, a lot to discover. I think again, we will find that all these discoveries will really have a practical impact also, in the, not only from a scientific perspective, but as I mentioned before, in our daily life. So with this, I want to conclude my presentation, and many thanks to Politecnico di Bari for the kind invitation, in particular to Professor De Tullio for organizing all this, and Professor Albino and Cupertino for the initiative and all that, for keeping me involved in this project over the years. So feel free to contact me and these coordinates. And right now I'll be happy to take any questions that you might have.
Thank you very much, Giuseppe. I have to say that your talk, from my personal point of view, was really interesting, since I am involved in the data analysis of the Fermi-LAT data. So I'm involved in the other part of the electromagnetic spectrum, while you showed your research activities on the infrared and the optical part of the spectrum. And for me, this talk was very interesting, since I learned a lot of things about the operating principle of a space detector for infrared radiation and optical radiation. So I would like to thank you for this. I have some questions from my side, but I see that there is a question from a participant to the seminar, Tiziano Santese. So probably it's better if he asks first his question, and then if there is some time left, I can add some comments and can ask you some more questions. So please, Tiziano, go on with your question.
Okay, here I am. Firstly, congratulations for the presentation and for your career. And I would like to know, I would like to make a question about your PhD, because I read something about it, and I can see that it is strongly correlated with what you are working on. And the question is, how much important is a PhD for a career in a space agency, in an important space agency like NASA? And the second question, if I can, is about the NASA Academy, how to enter in a such important competition and such important role in NASA, because I know that NASA vacancies are open only to American citizen or green card holders. So what can a young graduate space interested can do for applying to such important position? And that's all. Thank you in anticipate.
Sure. So I think when you get to work with such types of technology, I think it becomes very important to I think a PhD becomes very important because you are dealing with a lot of very complicated concepts and ideas that no one has ever really thought of before, and problems that are really, really challenging. And I hear really, this is not the result of just a few months of work, but James Webb has been in the making for over 20 years. So a lot of technology had to be developed, even invented to reach these results. So I think a PhD becomes important because that's really where you learn how to do research, how to really brainstorm ideas, how to solve problems, and you also are in institutions that allow you to work with the right facilities. And so I think it's definitely highly recommended. Now, if necessarily, a lot depends on the types of jobs that you are going to do. Also, not every engineer is required to do or to have a PhD. It really depends on your role on the project. Regarding my career, I think when I applied to the NASA Academy in 2009, the program offered 2 spots for European students at the graduate level. So I applied and I went through the selection process, and eventually I was selected as one of the 2 European. The other guy that came with me was a guy from Spain. And then and a little bit ago, the NASA Academy program was actually to develop the future leaders of the aerospace program. So we were 20 total. So the other 17 were American, and there was a French, sponsored by the CNES, the French space agency. So yeah, and then one lead things to the other, and again, I was offered a job after the NASA Academy from my boss at the time. So I mean, the NASA Academy right now is not really an option anymore for European students, because the European Space Agency is no longer supporting the program, unfortunately. But there are other programs that are open to non-American students. So I mean, there are plenty of opportunities out there.
Thank you, Giuseppe. I see that we have more questions. The first one is from Martino Pinto. So please, Martino, go on with your question.
Yes, so good evening, Giuseppe. Thank you. First of all, I wanted to say that I'm from Lizzano, so like you, and so very pleasure to have you. And I wanted to ask more, technical question. So, for example, the Hubble Space Telescope was kind of a Ritchie-Griffin optical scheme. Which kind of optical scheme is the James Webb telescope? Because I see it's a kind of simple Newtonian telescope, classical, but maybe inside there is some more complex optical scheme. So this is my question. Thank you.
Yeah, I cannot show it, but I mean, I can say that I'm gonna try to. Okay, here, yeah. So, like I said, it's basically reflective. So there are no lenses, just a reflective telescope, and you have all the mirrors that reflect the light inside, and then even inside it's even more complicated because you had to split the light so that it reaches all the different instruments that you can see here. You gotta get into spectrograph, mirroring, and all the other the four of them. So really, there are additional mirrors. So like there's a tertiary mirror inside, and then there's also a fine steering mirror for fine guidance purposes as well, and then the light really follows a lot of different paths inside that eventually allows the light to focus on the focal planes of these instruments. So I think you can find it on the internet. I think there is a picture that shows the complicated path that the light goes through before it reaches each of the instruments. I think it's available online. So.
Okay, thank you.
Okay, there is now a further question by Maria Cinefra. So please, Maria, ask your question.
Thank you. First of all, I want to thank you for your very interesting talk. And I am a structural engineer, and I'd like to understand how much is the design of telescope affected by the vibrations, because you mentioned some vibration test. I'd like to know how much is limiting this issue, this problem in the performances of the telescope and the design of telescope.
Yeah, sure. So I think the main issue here is that the rockets they shake a lot. Rockets shake a lot, and so that there is a lot of vibrations that the telescope feels over many frequencies. So therefore, I think the goal of this test was not to simulate that, and to see if the telescope could withstand the effects of these vibrations. So here I was really shaken along the three axes, X, Y, and Z, and over very different frequencies. And really the goal was like, okay, can exactly like say, can the structure withstand these forces, or is the telescope going to fall apart? So that was really one of the goals, and I think exactly the structure serves exactly the purpose, and I think some of the tests reveal some weaknesses in the structures that had to be addressed. Okay, clearly, there were some problems. So doing this test was actually like kind of eye-opening, because it showed us some areas that were weak and then need to be fixed. So so it was done, it was repeated, and then everything went well. So I think that's really why we do this kind of tests. So it is limited only as long as everything falls apart, but you want to build something that withstands such vibrations, and therefore really not it should fall apart during the test, or even more during the launch. Obviously, the tests were pushed well beyond the environment that usually is found in a rocket. Okay, to have some margin. So if James Webb can withstand such very rough conditions, that we feel safe that on the rocket where things are a little bit better, things will go well. And that's really why we have been spending a lot of time doing a lot of testing, because we cannot afford any mistake. Once we launch it, that's it. We cannot go like we did with Hubble 30 years ago to fix the mirror or whatever. So yeah.
Thank you. Thank you.
Sure.
Okay, we have further questions. There was Professor Vito Albino first, but maybe there are also two PhD students then. So Professor Albino, if you want to ask your question first, please go on. Otherwise, we can switch to the PhD students.
I have just a couple of questions for Giuseppe. First of all, thanks, Giuseppe, for your presentation. You give us a ride in the space, and it's a pleasure to hear and to see you. Unfortunately, not to meet you. Anyway, next time. As you know, I am a professor of management, not a professor of aerospace engineering. So my questions are related to managerial aspects related to the Webb Telescope project. Just if you have any estimate about the cost overrun of the project. I know that that's been a very expensive and complex project. So I don't know if you have an estimate of the cost overrun. And you mentioned commercial applications derived from the research and the development related to the telescope. So if you have any estimate of the global return of the investment, if NASA did that.
Yeah, okay. Yeah, sure. I think for the so the first question was about the cost overrun. So if I remember correctly, I think initially, like, you know, I think the estimated cost was like $800 million, and then it grew to like $8.8 billion. So like a factor of 10. It grew over time, and you know that was due to you know, technical challenges, due to the fact that, like I said before, you know, a lot of technology had to be developed from scratch. And so, you know, it just, and then the fact that we had to do a lot of testing on everything. So I think, you know, that was I believe that should be the final cost more right now, more or less. You know, you might have heard in the news that, you know, Webb went through several replanning phases over the years. So, you know, the initial launch date, you know, at some point, they were claiming it was going to be 2010, and then it got pushed, you know, back, you know, until we claim that, you know, hopefully, you know, will happen this year. But, you know, again, a lot will depend on how the final tests go. So that's will be the final estimate right now. Regarding the commercial, yeah. So I think I have this estimate here, $30 million in the revenue. Now I don't know if it's like global or only in the US, but that gives already an idea of actually how much Webb has been able to generate beyond actually its direct funding, as I have highlighted here. So a lot of, you know, new technology, new jobs, of course, and you know, in many different fields. I mean, this may be a little bit outdated. This figure here, I think, goes back to a few years ago. So it might have changed, but yeah, no, that's as far as I know.
Okay, thank you so much, Giuseppe.
No problem.
Okay, thank you, Professor Albino. So we have a couple of more questions. The first one is by Ahmed El Hussein. So please, Ahmed, go on with your question.
Okay, yes. First of all, thank you, Giuseppe, for the very, very interesting presentation. I mean, like, sophistication of the work done is, I mean, I have a lot of questions in my mind beyond measure, but let me just first of all thank you very much for this. I'm a PhD student here. I'm studying chemistry now, but I'm actually a microbiologist, so very different field. But that brings a question to my mind. But my first question would be a little bit technical. So you spoke about the telescope, the James Webb telescope. I wonder what kind of spectra do you obtain from that? I mean, do you obtain hyperspectral data or multispectral data, and what kind of that? And how, I don't know if this question applies or not, but how do you go analyzing these data? I wonder, you don't look at the photos and you say, oh, there's a planet here, a planet there. And the last thing, which was probably very interesting, is how do you work in this interdisciplinary team? Of course, when you work in space, it's a lot of interdisciplinarity, but usually, I mean, from my past experience, usually you get the worst of both. You work with a chemical biologist, you get like biologists who know nothing about chemistry, and biology know nothing about chemistry, and so
Yeah.
it's very particular. And yeah, these are the main questions. And I would also be interested if you tell us what are the most challenges, the most challenging thing that faced you during your work. So
Yeah,
thank
sure.
you very much. I'm sorry for my long questions, but it's very, really interesting to me. Thank you very much.
Okay, no problem. So I have a table here that shows a little bit. So Webb will work in the near and medium infrared. As I said, we collect spectra between 0.6 and 29 microns. Yeah, the short end is limited by the mirrors gold coating, and then in the long end by the detector technology. In particular, I think near spec, the near infrared spectrometer will work. So we'll collect spectral data between 0.6 and 5 microns, whereas the other instruments will collect basically the light between 5 and 29 microns. That's how they're going to operate. They are, I think, medium to low resolution. Pretty much all of them. I think MIRI has 2 different ways of operating, like one at low resolution, one at medium resolution. So that's a little bit, gives you the idea of the spectra that we'll be collecting and which instrument will do which. And then I think, let's see, the second question was, is that working in a multidisciplinary team? Yeah, it's definitely very challenging. So for Webb, I actually joined the thermal engineering team. So I had been assigned to that team to do thermal modeling. So I worked with a lot of thermal engineers back then, and I was very very fun for sure. But then we had to interact with the other systems, of course. The thermal system is really the most critical system for Webb, given the very low temperatures that we're going to have to deal with. So the requirements were very, very stringent, and it was very challenging to working on all the modeling and then collect the data, do tests, and then kind of validate the model with those data. But for sure, I mean, also from my experience in working in other multidisciplinary teams, I think probably working as a systems engineer allows me to really interact with pretty much every system. Not only thermal, but like optical, structural, attitude determination, control, propulsion, and so forth. And it's very interesting because in a way, my role is kind of be a little bit really a little bit of everything to be able to put together the big picture of the these system of systems and then make sure that every system not only works independently but works together with all of the others. So it requires a lot of daily interactions with work on Exclaim or Prime. I have to interact daily with every subsystem lead. Be on top of everything, and then we use a lot of practical like systems engineering methodologies that allow us to quantify all that we need to work with, and then look at the numbers and make sense of them and come up with I don't know, like risk plans or testing plans and so forth, right? Depending on where in the mission life cycle you are. So there's definitely a lot of interaction. What I like about my job is that I get to learn a lot also from my colleagues, especially those that are really like the experts in their own field, and it kind of challenges me to always be on top of everything every day. I'm forgetting the third question.
Which was your last question, Ahmed?
No. This is, you answered all the questions. That is right, right? Because one question was like a double-faced question. Thank you very much. Thank you very much.
Okay, great.
Thank you very much. So we have our last question by Huang Ximeng. So please, Huang.
Thank you, Giuseppe. It's really an impressive project. And I'm from Politecnico di Milano, and I have some curiosities about the attitude control of this mission. So I was wondering if the telescope needs to reorientate from one direction to another, and if so, how do you control such a large flexible structure, and is there any advanced technologies implemented in terms of for example, the actuator or the design of the controlling system? And actually, another curiosity is also about the vibration. If in case of the reorientation, that maybe some vibration may happen, and if so, how long it would take to reduce the vibration? That's all my curiosities. Thank you.
Yeah, sure. Yeah, sure. Right. So, so the attitude determination control system is mainly consists of so different sensors. So you'll have star trackers, sun sensors, and gyroscopes. And then you basically have that's for the determination, and for the control, well, actually I use the reaction wheels and thrusters. Okay, so mostly the reaction wheel are gonna be those that are gonna be used to change the orientation of the telescope in space. So to perform all the necessary slew maneuvers that the telescope will have to perform, and then the thrusters will be used to do to dump all the momentum, the excess momentum that accumulates into the reaction wheels. So it's got like different kinds of thrusters, but basically 8 monopropellant thrusters hydraulically, and they will perform this kind of momentum dumping. And then we got a few other thrusters, bipropellant thrusters for actually orbit station keeping maneuvers. So that's really a very brief, quick overview of the attitude determination control systems of James Webb. So then regarding that there will be vibrations, so on, that they need to be kept under control, of course. So I'm not allowed to share the number publicly, but that will be clearly like some time to kind of allow those vibrations to kind of damp out. But I think in general, what I want to emphasize though is the fact that Webb is like event driven, so it will be very, very autonomous in its way of operating. So like I think on a weekly basis, you will receive a lot of the plan for observations. So you will know what to do, what to look at, and how to move in space fully autonomously. But should, for example, even the reaction wheels kind of will be kind of moving so that will point the telescope where it needs to point and so forth. But should something happen that, like say for example that the reaction wheels have accumulated too much momentum beyond what had been planned, then they will have to stop that observation, dump the momentum with the thrusters, and then kind of move on to the next observation. In the meantime, you will communicate to Earth to say, hey, I was not able to finish that observation. And so the next round, when they re-upload all the commands, then they will go back to that observation had been left kind of suspended, and it will it will do it again at a later time. So there's a lot of I think automation and like I said, even event-driven operations in Webb, which is really amazing.
Okay, thank you very much.
Yeah.
Okay, so we have a final question from the YouTube live chat from Roberto Musaio Somma, who is asking, could you elaborate on how the James Webb Telescope will be maintained?
How will it be maintained? So Yeah, I mean, once it's out there, it's just be on its own. That's why it's got a lifetime of 5 years nominal, but up to 10. Because the orbit, like I said, is unstable, so the only thing that we can do is like to use some of the fuel to to do orbit station keeping. But once the fuel runs out, then that's when Webb will finish its life. Basically, I mean, it won't be able to really be in the orbit where it should be. It will start kind of drifting away, and so it's a little bit dead. So once it's out there, it's out there. We cannot do really much from Earth. So we don't plan to send any robots or any astronauts to fix things or anything. So everything, I mean, should be able to do it on its own. Like I said, the sun shield will have to protect from thermal radiation, but also from the micrometeoroids. So that's all. That's what the sun shield is for. So it's all passive in a way. Like I said, very autonomous. There will be nothing we can do from Earth to improve, its capabilities or to kind of fix any problems that we might have. Unless, I like to say always, maybe in 10 years, we'll have robots capable of maybe do that for us. Who knows? Never say never. But right now, like I said, that's not the plan. So.
Okay, thank you, Giuseppe. I had a question on the detector, but I was anticipated by Wang. So I have just a final remark. And the remark is the following. Basically, what we have learned from previous experience is that the universe should be observed in what we call a multi-messenger context. Multi-messenger means that we have to look at gamma rays of different energies. So you discussed about the visible and infrared part of the spectrum, while I'm personally involved in the analysis of gamma rays, and there are also observations in the X-ray bands, and also in the radio band, of course. Multi-messenger, however, means also charged cosmic rays and means also gravitational waves. So my question is, which are the NASA perspectives in these fields? Are there any future detectors planned to look at X-rays, at gamma rays in a different energy interval than Fermi? Or are there any planned missions for space-based interferometry for gravitational waves?
Right. So, okay. So for space-based interferometry for gravitational waves, yes, the LISA mission is for now a concept actually led by the European Space Agency that we will do exactly that. Space-based interferometry for gravitational waves, but it's not planned to be launched in before the 2030s. So we still have at least 10 years to go before we can see it. But at least a Pathfinder already made a lot of kind of technology demonstrations in the sense. So yes. And then in terms of detectors, so I talked about LUVOIR here. LUVOIR stands for, again, UV, so ultraviolet optical IR. And another concept is links. So links will work in the X-ray band, but like for that, I mean, I think for example, think about the detectors there are things about like TES, so transition edge sensors, so microcalorimeters. So that kind of detectors, for example, for X-rays. And for LUVOIR, I think when we think about something LUVOIR, I mean, I think the challenge here is really like how can we develop large format detectors with thousands of pixels. We already pushed the envelope with James Webb. I think we will need even more for something like LUVOIR. So that's really where NASA is kind of focusing on right now. So really large format detector arrays for such future missions, and we have a lot of technology development progress ongoing, and I think there's definitely a lot going on in this area. But I think we need to wait really fewer months to hear from the National Academy of Sciences to hear about which of these concepts will be actually prioritized for the next decade, and that's where NASA will most likely welcome that those recommendations and then decide to focus on these future flagship missions. So Roman was the #1 priority for the 2020. James Webb was back in the 2000, I think, decade, and Hubble was for the 1990 decade. So, once we hear back from the National Academy of Sciences, we will know, what we are going to prioritize, and NASA will put everything, funding and effort, to work toward those priorities. And I'm really talking about the flagship missions here. There will be other, smaller missions as well that will be prioritized. Hopefully, like you said, they will cover a little bit the entire spectrum, because multi-messenger astronomy is really the future, as we would see, in the past, in the recent past, with all the discoveries that have happened, also thanks to the gravitational waves.
Okay, thank you very much. So I think that we are at the end of our seminar, and I think that there is our magnifico lettore, Professor Cupertino, who wants to
Thank you, Francesco.
So please, Francesco.
Yeah, thank you. Sorry if I'm late, but it was important for me to thank Giuseppe Cataldo for his availability. Finally, we made it. We tried several times to organize something at Politecnico di Bari. Now we are welcoming you, not yet in person, but hopefully in next future. As soon as you will come back in Italy, it will be my pleasure to welcome you again at Politecnico di Bari. It is, since I know you, and I know something about the subject, for these reasons, I think that your contribution is very focused on the title of our series of events, Rediscovering the Space. So you are discovering maybe something really new in the space with your research, with your activities. I think that this kind of subject is really inspiring for our students, for our PhD students. That is the main reason why we are here. We are trying to give value to these PhD courses that we started just with this year, together with Politecnico di Bari and the University of Bari. And I'm really happy that the success of the series of seminars is being confirmed also by this event this afternoon. So I do not add anything else. I want just to thank again Giuseppe for his contribution, and Francesco and Marco for their effort in the organization of the seminar. I give back the stage to Marco, maybe for the final remark and a few words about the next seminar, maybe.
Okay, thank you, Francesco. Yes, I really want to thank Giuseppe for this inspiring speech, and I'm sure the speech is fascinating many of us. You gave us the opportunity to look things from a different window than usual. So thank you. I also want to thank everybody for participating despite the difficulties related to this telematic mode. But all of us hope to see you in person, you and all of the other speakers in person. But at the moment, we are strictly connected to the computer. So the next event would be the seminar from Valentina Sumini, but I want to anticipate that maybe we will have a seminar with the JPL, people working at JPL related to the Mars mission on the 12th of March. So the details will come soon, Francesco. We are just concluding the organization. So Giuseppe, thanks again. Hope to see you soon.
Yeah, my most heartfelt thank you to all of us, really, for having me, here as a guest. And it's a pleasure to see all of you, although in virtual mode. And I really hope to be able to come back to Puglia and Bari very, very soon, and be able to see you and meet you all in person. So thank you again, really, for this opportunity.
Bye-bye, Giuseppe.
Bye, everyone.
Ciao, Giuseppe.
Ciao, Vito.
Ciao.